Okay, this one? You got Divergent on,
Yeah.
okay, on the right version, right? Yeah. Okay, so you got, this is improper, so we let b approach negative infinity, and um, and then its antiderivative is itself. We'll do that all in one step here. So b here, ln of 2 here. Plug everything in. So e of ln of 2 is 2.
I see why I got it wrong.
Oh, okay. And it's because of that negative infinity, right?
Yeah, I put e to the negative infinity and I thought it's negative infinity, not zero.
Yes, and I'm gonna
Yeah.
make that point even yesterday. I don't know if Heather's here too, but it's those subtle differences that like throw the whole problem. The other one, she's not here, but she had asked a good question about being over zero. Like when something is over zero, that's the other one that I keep. I know this one is also for that subtle difference as well. You guys want to think of it of a limit where you're approaching zero and it's in the denominator as like 1/1,000,000, which when you flip that becomes like infinite or a million, a really large number. So it's not undefined, it's infinity. And then therefore, if it's an improper integral, you would say it's divergent. So anything else on the maze, since we're on the maze? You guys did okay on it? I would say if you guys get a chance and you want extra problems, again, do the other problems that weren't part of the maze, or sorry, part of the pathway of the maze, some of which are much more challenging, I think, than the pathway that led you to the answer. Um, anything else?
Can you go over 7 on page 10, the review?
Sure. Oh, wait, wrong file. Oh, okay. You guys had one where you had a sign one. I don't know what assignment it was, where you let it go to infinity. And if you guys think about what sine and cosine does as you go out to infinity, it bounces back and forth, or we say it oscillates, where it doesn't actually go to a particular value. So the limit, it doesn't grow to a very large value, like when we're discussing relative rates of growth. It's just back and forth between -1 and 1. So if you think of this really as like we're looking at what happens when we go out to infinity. If we're looking at this in terms of rates of growth, here you have something on top that oscillates between -1 and 1. ln, as it goes out to infinity, is a really slow growing, but still infinite growth. So if you have a larger growth on the bottom, no matter what the top is doing, what is this limit approach? So if you have like a really fast growing bottom, what do you guys have? Any ideas? Yes. Okay. So larger bottom is 0. So think over 1/1,000,000. So this one is 0. So think of relative rates of growth on that problem.
Can you do number 4 or number 6 on this page? It's 1 to the infinity.
Yes. Okay. So I think Tessa, you had asked if you needed to know the caterpillar ones. You guys do have a few questions on the caterpillar type questions. And yesterday at tutorial, I had mentioned that the pattern or the overall theme that you want to notice with the caterpillar problems is that you have an indeterminate form that is exponential in form. So you have something in the exponent, and what you want to do whenever you have anything other than 0/0 or infinity/infinity is to get it back into that form. And so the first thing you do is bring the exponent down. And so in order to do that, if you have any one of these caterpillar forms, is to take ln of the expression. So I would say the ln goes here, and then you want to think of the e as undoing the ln so that you're really not changing anything. And then anything that is in the exponent is going to get brought down in front of ln. Okay, so you kind of want to keep in mind, don't forget the e, that's the mistake part. And then you have 1 over 1 minus x, and then ln of x. So if you plug in 1 at this point, so you remember, you want to keep in mind, you get back to 0 over 0, infinity over infinity. What is one thing you guys can do to this as you see it to make it a fraction? Simple move would be, let's see what happens if we just make ln of x on top, right? With the 1. So you have ln of x over 1 minus x. If you plug the 0 into here, sorry, if you plug the 1 into here, you guys get 0. Plug the 1 into here, you get 0. So there is where you guys get the 0 over 0. So at that point, 0 over 0, you're ready for L'Hopital's rule. So it's just forcing it to be in that form so that you could start applying L'Hopital's rule. And in doing so, you take the derivative of the top, which is 1 over x. The derivative of the bottom is -1. You've got this e on the side. The limit is part of the exponent. And so when you plug the 1 in, you get 1 over -1 or just -1. So the correct answer would be e to the -1. So we'd say that one is, it actually exists. Does that make sense, Tessa? So this step right here, after you move the exponent, move the exponent down in front of ln, rewrite your expression so that it's either 0 over 0 or infinity over infinity. Then L'Hopital's rule from there. Don't forget this part. And then that's pretty much it. That's the only, extra step you have to do with the caterpillar ones. Question, we cannot do L'Hopital's rule for number 7. Yes, because the top is a finite. Yes, so, well, actually, technically, this is just cosine. If I asked you what it was as it goes out to infinity, it doesn't really land upon a number. So the limit doesn't really exist in the sense that it goes towards a specific value. And so when we're comparing it to, I guess if it was the limit as r goes to infinity of just, sorry, I'm thinking you guys can see my finger, but you can't. If you just had cosine of r like you did in another problem like sine or something, then I think you did a problem similar to that, and it diverges or it does not exist. So it doesn't exist, and if you're just viewing the limit of cosine as it goes out to infinity. But when we go out to infinity and we make it a fraction, we're saying what is the growth rate as you compare the top function to the bottom function. And so going out to infinity, this is going to be insignificant in growth, whereas the bottom is infinity. So we can make a conclusion that it's finite. It's going to be 0. Okay, yeah, kind of a confusing concept on that one. How about, and then you guys don't forget the other indeterminate form was infinity minus infinity. So for those ones, again, like when you have the caterpillar, force it back into 0 over 0, infinity over infinity using the ELN. When it's infinity minus infinity, force it back into the original 2 by rewriting it as one fraction. I recorded a video, if you haven't seen it already, on 17, because that one was kind of difficult. Don't expect that you guys will have one like that. That's not going to be on the test, something that complicated. I would expect you guys to know, I think at most the level of difficulty would be like those inverse tangent ones where you guys have to make an adjustment to the input to figure out what it is, like arctangent of like x over 2 or 2x. There is a question on just in case, would partial fraction? Yes. So partial fraction is on it. And you guys looking at 13 through 17, which one of those would require partial fraction decomposition? 13 through 17 that you see there. Yes. Okay, so I saw 15, so 15 for sure. Basically, if you guys have a polynomial on the bottom that you can factor, take out the x for that one. So x times x minus 2, you're going to have to use partial fraction for that one. 17, watch the video on it. It's not straightforward. On that one, it's actually an inverse trig function, that one. Not really, I know. It's kind of ugly and not a very straightforward question. The rewrite algebraically, the hint to you guys is if you want to start it without actually watching the video, I would say multiply the top and the bottom by e to the x and see what you guys get from there. See if you guys can figure out what inverse trig function it results in after you do that multiplication of e to the x over e to the x. And I think you guys can get it from there. If you distribute and just see what happens with that.
Ms. Kim,
Yes.
do we need to know how to do limits comparison?
Okay, good question. It's not a huge focus of this chapter, but I would have an understanding of the basic ones that we went over in the notes and, you know, having an idea of like the P series, like if I gave you guys, and, you know, my mind is on series already as we move into the next one, but like 1 to infinity, and then you had something where you guys had x to the third power, something similar to that. But it wasn't just x to the third, it was like x to the third plus 1. Having an understanding that you would want to compare that to 1 over x cubed and make a conclusion that it behaves the same way. And really it's, you know, after you guys do a few of them, you should have an idea of like, okay, if it's going to be similar to x cubed, and you know that in that sense it converges, that anything, if you're going to add a constant to it, it's not going to change it when you're looking at overall growth. So it will result in a constant when you're doing the limit comparison test to it. And so we would expect like something like this would converge. But so just that basic understanding of it, so at most 1 multiple choice. I'm trying to remember if it's on this test or on the next test if I just skip this altogether. So I wouldn't like have a huge focus on this. The focus should be on L'Hopital's and improper integrals, partial fraction decomposition. It's really just those 3 topics. And then if you guys had trouble with the free response today, in terms of remembering, maybe not D, but just in remembering volume and cross sections, maybe look over that again. That might come into play for your free response. There's a question on 8 and 9 on this page. Okay, so 8 and 9, you guys have that when you do an initial plug-in of this. So first you guys have plugging in pi over 2, secant of pi over 2 is the same thing as 1 over cosine of pi over 2. So you've got 0 here, and then 1 over cosine of pi over 2 is 1 over 0. So times 1 over 0 like that. So essentially you guys have improper, or sorry, not improper, but indeterminate form. So I would change this so that it's the indeterminate form I would expect by doing, and by the way, 1 over 0 is interpreted also as infinity. So that's an indeterminate form when you first just look at it as just 0 times infinity. And then what we do is we change it back to the original. Remember always to go back to 0 over 0 or infinity over infinity. For this one, you would just do a simple move of changing this to be cosine of theta on the bottom. I think you can take it from there, but let me know if you're still having trouble processing that, because now you guys have 0 over 0, and you just apply a derivative on the top and the derivative on the bottom, plug it back in for that one. And let me know if it still doesn't make sense to you. But at this point, again, apply the derivative separately for that one, and then for that one, then do the plug-in again. It might result in, yeah, so I think you guys should be able to get the answer from there. Yeah. Off the top of my head. Oh, let me come back to that question, Angelina. Let me answer this question first. There was another question on number 9. For number 9, again, when you guys plug in 1 into here, you guys are going to get 0. 1 into here, you're going to get 0. So 1 over 0 is infinity minus infinity, in which case we're going to rewrite as one fraction. to try to force it back into 0 over 0 or infinity over infinity. So common denominator is x minus 1 and ln of x. So we're going to do ln of x minus quantity x minus 1 all over x minus 1 ln of x and limit as x approaches 1. You can at this point plug back in again. So at this point, I haven't really done anything except for rewrite as one fraction, but if you guys do, you'll see that you still get 0 over 0, which now is what we want, right? So L'Hopital's rule, we always want to go back to the original 2 that we learned. And once we're there, we apply L'Hopital's rule. We're going to take the derivative of the top separately from the bottom. So 1 over x minus 1 all over product rule on this one. So the derivative of x minus 1 is 1 ln of x, and then plus x minus 1 over x. Okay, so at this point, highly recommend you guys rewrite it as a clean fraction where you don't have fractions within a fraction before you evaluate. So the easiest way to do that would be to multiply the top through by x and the bottom through by x. In which case you guys would get limit as x approaches 1 of 1 minus x on top. So distribute. On the bottom, you guys would have x ln of x plus x minus 1 when you distribute the x to those two terms. And then do the plug-in again, and we get 0 over 0 again. So then that means you guys have to apply L'Hopital's rule again, which is, I can see the end here because when you guys are doing the L'Hopital's rule, hopefully you are looking ahead and thinking, okay, well, you know, once I take the derivative of this top function, it's going to result in something that is not 0, which is good. So when I take the derivative of that, I get negative 1 on top, product rule and such at the bottom. You got the derivative of x is ln of x, or derivative of x is 1, ln of x plus x over x, which is 1, plus another 1. Plug the 1 in, and then we see our end in sight, negative 1/2. Oh, thank you, Tessa. Oh yeah, no worries, you guys. Tutorial's just open to you guys coming and going. Yeah, let me know tonight if you guys gotta go. If you got questions, I guess I'm back on at 3:30. If you guys you go on your own and you guys have extra questions, feel free to join. Is there anything else you guys want me to go over? Partial fractions, do you guys remember? Partial fractions?
Can you do number 15?
15. Oh, the partial fraction one.
Yeah.
So I would do this one of two ways. Like one, if you guys don't want to forget the improper part, I would do b to infinity or limit, set it up as a limit problem. 3 to b of 2 dx over x squared minus 2x. Rewrite that as, so on the side, I'm going to do the antiderivative. Maybe more off to the side next time, but antiderivative here, you got 2 over x squared minus 2x, just the partial fraction parts. You guys have that, this should be a over x plus b over x minus 2. So factor the bottom, figure out what the two factors are. Imagine that you're asked to put the two fractions on the right together as a single fractions. What would the step be? The step would be taking a times x minus 2, b times x, and in theory, that numerator should be equal to 2. You set x equal to 2 to cancel out the a. If you set x to 2, that means you have 2b equals 2, or in other words, b is equal to 1. In the case where you want to eliminate b, you would let x be equal to 0, and when you plug in 0 here, that's 0. Then you end up with negative 2a is equal to 2, or a is equal to negative 1. Plug all of that back into here, and you have negative 1 over x plus 1 over x minus 2. Integrate that individually. So you have, once you come back to your limit as b approaches infinity of the antiderivative, which is, don't forget to take the integral. Sometimes people do the whole partial fraction part and think that that's the antiderivative. You still have to integrate. So when you integrate that, you get ln of x minus 2 minus ln of x. I would suggest that you guys rewrite the x minus 2 over the x as a single, not I would recommend, you have to do that in order to evaluate the limit correctly. So rewrite it as a single fraction and then plug your b in and plug your 3 in. You're going to get ln of b minus 2 over b minus ln of 1/3. Okay, this is the part that's, oh boy, I forgot who had asked about L'Hopital's rule within an integral question, but here it is. When you let b go to infinity, you technically have infinity over infinity. Okay, so this part right here is infinity over infinity, which is, when you take the ratio of it, is, think of rates of growth, that's just 1. b minus 2 over b is just 1. Take the derivative if you liked for L'Hopital's rule, but you get basically ln of 1, which is equal to 0. So your answer is negative ln of 1/3. Just as a side comment, if you don't see negative ln of 1/3 in a multiple choice answer, be aware that they might do things like move the -1 up on top there. And so ln of 1/3 could be equivalent, or sorry, 1/3 to the -1 could be equivalent to ln of 3. So like log rules for that. That's a good question.
Thank you.
Uh-huh. Any other ones you guys have questions on? And I think if I went too fast on something and you guys want to go back on it, I will post this video. Someone already asked me, they can't make it to tutorial. So if you guys want to go back on a question, I'll post it and I'll share it on Remind. Any other questions you guys have? Michelle, I haven't heard from you. You're doing okay? Annie?
Yeah, I had my question answered already.
Okay. All right, so trying to think of what else. Again, look back at the volume stuff. It feels like we're a little rusty on that, an area between curves. And then aside from that, just, yeah, don't forget the whole infinity thing and negative infinity stuff that I know it could mean the answer between divergent and 0. So just be careful with that. Make sure you guys are putting things in the denominator if it's a negative exponent. So it's a little bit more clear to see that it's equal to 0 when it's going out to infinity in the denominator. Let me know, you guys, if you get stuck on another problem, I'm happy to record a video and share it with you. Okay. And then if you go off and do your problems right now in the next half hour and you need to hop back on, let me know as well. Or you don't have to let me know, just hop back on. Okay, guys, I'll see you later. Good luck studying.
Thank you. Bye.
Bye.
Yeah.
Oh, Miss Kim, I forgot. I think you went over this earlier, but for number 7 on the maze worksheet, I think when I do it, I saw that 1 and 0 are both vertical asymptote, and then I got stuck. I don't know what to do from then.
0 are both vertical asymptotes. Oh, you're right. Yeah, they are. So ln of 1 and 0 is also, so you would split the integral.
Is it okay if I just put 0.5 for like the
Yeah.
middle?
Yeah,
And then,
value.
okay.
Yeah.
That's what I'm planning to do.
Okay, did you get divergent at all for that one, or what was the answer to that one? I'm wondering if it was, oh, okay. You're gonna replace one of them and it will be divergent. So
Okay.
yeah.
Wait, so the answer is not correct?
Isn't the answer divergent for that one? Let me scroll down to the answer. Yeah, so it's divergent.
Okay.
Yeah.
So I just split up the integral and make it from b to 0.5 and a to 0.5. Okay.
Yeah, so then when you examine it at 0, I think you're gonna get it's divergent anyway.
Mhm.
So then you means you don't have to do the other one.
Oh, okay, got it.
Does that
Okay.
make sense? Yeah.
Yeah, that makes sense. Okay, thank you.
You're welcome. And Christine, you had a question on number 5 on page 9. How do you determine if it's convergent or divergent? Is this page 9? You have to actually go through with the whole integral, like, so you'd have to replace the infinity, rewrite the improper integral, basically evaluate the integral, and then go from 0 to b, and then integrate. So then your first step on an improper integral is to integrate that. So if you integrate that, you get e to the negative x, but you have to undo the chain rule that you would have had here by timesing by the reciprocal of -1, which is still -1. And then plug in the 0 and the b to see what you have. So on this one, when I plug in the b, I'm going to make note of the fact that that's a negative exponent. So I'm going to put the e down below. So for this one, I have -1 over e to the b, and then minus whatever I have when I plug 0 in. So minus a negative is going to result in a positive, and then 1 over e to the 0. Then at this point, when you plug infinity into here, so you still have to do the limit. So as you let b go to infinity, you have a big bottom. So that's going to result in 0 for this one. And then 1 over e to the 0 is just 1. If you get any sort of number as your answer, that's convergent. If you get infinity or negative infinity, you get divergent. So you do have